はい。軽く喋ってます。おはようございます。暑い。バーチャル背景やめればいいのか。
Hello, my name is Kevin Dice, and today I'm here to talk to you about Prettier for Ruby. I work at Shopify. I'm based out of Boston, Massachusetts, and the question I'm here to answer today is, what is Prettier? So Prettier is a JavaScript package that provides a language-agnostic framework for building formatters. So what does that mean? It provides specifically a set of language-specific parsers, a parser for each language that it supports, and it provides a way to take that information from each language-specific parser and build a Prettier-specific intermediate representation. That means that it goes from language-specific to language-agnostic. It also provides a printer for taking that intermediate representation and printing out the formatted code. Finally, it provides a suite of editor tools and plugins that enable all kinds of better workflows like formatting on save, formatting on commit, and in general, just standardizing the format of your code base across all of your developers so that we eliminate the need for a lot of conversations like which specific linter rules to enable, when a lot of the time it's just handled by these kinds of formatters. So out of the box, Prettier started as a JavaScript printer, and so it came with support for all of the various JavaScript implementations and variants. Later on, it developed language support for HTML and all of those flavors, CSS, and Markdown. Now, these are the formats that ship with Prettier by default, but there's additionally a wide ecosystem of plugin support, and that includes Java, PHP, Postgres, Ruby, SVG, XML, Swift, and this is actually a subset. Some of these are community plugins. They live on other people's GitHubs. The official ones live within the Prettier organization on GitHub. Today, I'm here to talk to you about the Ruby plugin that I've been working on for about 2.5 years now, and it's both a Ruby gem, it's published to rubygems.org, and a node module, it's published to NPM. It's averaging about 20,000 downloads a week, and it's under constant development when I get weekends to work on it. So let's talk about the way that it works. Overall, what it is doing is formatting your source code. What this means is it's converting source Ruby code into a concrete syntax tree. You might hear abstract and concrete, the difference being that it has specific information about where the nodes were placed in the tree and specific information about the source. We then go and attach all of the comments to the tree that we found. These are, source code comments. We place them into the tree where we think they belong. We then walk that tree and convert it to a different kind of tree, which is the Prettier intermediate representation. We then hand it back to Prettier and say, go print this. Prettier has rules around how to print its own tree, and then it will go and get rid of go and print out the formatted result. So just to see it in action, this is poorly formatted or well formatted, depending on your perspective, Ruby code, which then passing through the Prettier package will give this output. So much more easily understandable and readable. So let's talk about what's happening here. The first step, as I mentioned, is converting the Ruby source into a concrete syntax tree. And what that means is we're going to spawn a process that runs Ruby. Remember, this is a JavaScript package, so we're spawning a Ruby process separately that's going to be acting as our parser. And we're going to run it through Ripper, a standard library package that will give us the syntax tree. We're going to add some extra information onto Ripper that Ripper doesn't itself track, but we're going to need to track some extra information, which, for instance, location information, excess commas, things like that. And we're going to specifically maintain the list of comments and their source location from the original source. So this is what the code looks like that spawns the process. You'll notice it disables gems. That's just for speed. You'll notice that we're passing the text that we're trying to pass over standard into our child process, which is our Ruby process. And eventually we return, at the end of this function, we parse out the standard out of the child process and return it as JSON. So what we're providing as this contract for this Ruby process is on the input, we are going to hand you Ruby code. On the output, we want a syntax tree in JSON format. It's worth it at this point to take a little side moment to talk about how Ripper works and how we're going to use Ripper to work. Specifically, you can require Ripper at any time as part of the standard library, and you define a class that inherits from Ripper. Once you have that class, you can define these on methods, on event, and these represent each node inside of the syntax tree. Now, each node is going to have this method called whenever it gets to a node that is like that in the source tree. And they have different numbers of arguments depending on the type of node, but a binary specifically will have a left and a right node and the operation that's being performed in between them. And for this example, we're just going to print out what we're getting just so you can see as an example what's happening. So we can create our own parser and call parse on it, and we get this result to standard out. We get 1 plus 2. So you can see how that kind of information gets built. But obviously this isn't enough information for us. We don't know where any of those nodes came from. So we want to provide much more information, much richer information back as part of our syntax tree, back before we return it to Prettier. So we're going to loop over every single scanner event, which you can think of like literals or spaces or just tokens. And then each of our parser events, which are nodes in the actual tree, and we're going to define an explicit base method for each of those nodes. Then, when we want to track additional information or modify the tree in some way, we can just push more data into those base methods and then extract that into the syntax tree. What I mean by that is, for instance, there are a lot of nodes in the Ruby syntax tree that act like a linked list. They have one base node and then everything points to the next node. So you get a very wide tree. And what I mean by that is that things like words will have words new and then words add, words add, words add. So in this module, which is part of the parsing tree, or part of the parsing code, it actually changes the definition of those to instead just return a list. It just makes it easier to join with new lines or join with commas. Another time that we want to add additional information is when we have something like a multi-assign. Multi-assign can potentially have a comma at the end of the left side, which actually fundamentally changes the nature of the assignment and can change depending on splats and left and right numbers inside of the multi-assign. So we need to track that extra information. Finally, Ripper doesn't report comments back into the main tree by default, so we need to track those comments ourselves and keep track of the source position so that we know which nodes to attach them to. Finally, at the end, we're going to attach all those comments to the top level of our tree so that we can handle them in the next stage of processing. At the end of the parsing process, we're going to return JSON.fastGenerate response. We're going to return that JSON blob that we've generated over standard out so that our parser can then go and read it and hand it back to the node process. So the next step in the process is going to be attaching the comments to the concrete syntax tree. And so what we're going to do for each of these comments, we're going to walk through the tree and find the closest node to the source location for that comment. We're going to provide guidance to Prettier on which node to attach it to based on the preceding node before the comment, the following node after the comment, and the enclosing node, which is like the parent node. So you can think of this like if we had a comment on the 2 in 1 plus 2, and we had a binary node overall, the binary node would be the enclosing node. The preceding node would be the 2, and the comment would be after that. So we can provide guidance to Prettier. This is just a small simplified excerpt from our plugin information that we provide to Prettier for our printer. We say, okay, we don't want to attach comments to args nodes. And in order to get the child comment nodes, this is how we recurse down our tree, and this is how we print a comment. Remember that Prettier is language agnostic, so it doesn't have any concept of how to print a comment. In C, you would need 2 forward slashes there. In other languages, you would have other ways of delineating comments. In Ruby, of course, we have to have a pound sign. Finally, when we're providing Prettier with guidance, we can actually override specific behavior for how it finds the nodes it needs to attach to by reflecting on the nodes after they've been parsed and then determining where we want to attach that comment. And this can override the default behaviors, so we can provide very fine-tuned guidance for you can only put a comment on this node in this circumstance. All right, now that we've got a syntax tree and we've got the comments attached to them, the next step is going to be to convert that syntax tree into a prettier specific syntax tree. And you can think of this like creating Prettier's language. Prettier has all of these fundamental concepts that they call doc builders, and those are just nodes in the syntax tree. And what we're going to be doing is building up those nodes to build up this tree that represents a language agnostic version of our source code. So the most important node in the tree is going to be the group node. The group node tells Prettier that this is a atom, this is a transaction of nodes, that if it were to hit the end of the line, then you can actually break it into two different kind of node, and you can make it so that it will print differently when it gets shorter. So in this way, we can handle long and short lines like that. Finally, we are going to provide line suffixes, which is to say, no matter what breaks in the group, no matter what changes, this comment is always going to be at the end of the line to make it so that we support comments appropriately. So that was all very abstract. Let's go through a specific example. This is taken from the Prettier plugin for Ruby source code, and it is the function that handles printing out op assign. And what op assign means is if you have like or equals, and equals, anything like that, operator assignment. So these nodes have three children. They have the variable that is being assigned to, we have the operator that is being performed, and we have the value that is being assigned. And what we're going to be doing is requiring from Prettier the document builders, the doc or the nodes in the abstract syntax tree. And in this case, we're requiring just 4 of them: concat, group, indent, and line. And you can see what we're going to be doing is first we're going to get the value out of the node. Then we're going to put the variable that's being assigned, a space, and the operator. Then we're going to have some special behavior. That line node inside of the Prettier tree, if it's on the same line and it all fits, that's going to become a space. But if it breaks, it's actually going to become a new line. And so we can use this behavior to our advantage, where if it breaks, it's going to indent everything one level, so in this case 2 spaces because of Ruby. And if it doesn't, then it's just going to end up being a space. Finally, we can group everything together so it knows that this is an atom that can be broken up and depending on the line length. And we'll return that function and register it in our list of nodes and how they get printed. And if we go to the command line and we run bin doc, which is a utility binary inside of the Prettier GitHub repository, it will show us the Prettier nodes that get generated, not the Ruby syntax tree, but the Prettier syntax tree, and how that gets generated. And you can see from here, this largely represents the exact code that we have called. The concat gets replaced with an array and so on, but the important thing to remember is the left side of this is language agnostic. Prettier has no concept of the fact that foo is a variable in this case. It just knows that foo is a string that it needs to get printed, and it has rules around how to go and print that. The final step is to take this tree, hand it to Prettier, and Prettier can go and print these out. And Prettier takes care of this for us. So this is one of the benefits of building within the Prettier ecosystem, is that we get to take advantage of all of the work that has been done on this for all of the other various languages that have already been built for this. So what we're going to do is walk the Prettier tree, and this is inside of the Prettier package. At each node, it's going to call the correct print function, which nodes can have different print functions. And then if you hit a line limit, then you're going to break the outermost group and shift it back. To give a concrete example of what this looks like, let's look at this small Ruby segment that has an overall op assign node. And what it's doing is doubling the value of a list of items. Let's say that our line length was actually much shorter than 80 characters. It's whatever it is, and this is too long. What we're going to do is the outermost group of this tree is an op assign node. So we're going to break the op assign node as we saw earlier. and it's going to move that outer value in. Now, let's say that this is actually still too long. The next outermost group that can be broken is the brace block associated with the map call. And so what we can do is we have provided rules inside of Prettier. Okay, this is too long, so we can go and convert it to a do end block. And so what Prettier will do is, as the maximum line length grows and shrinks depending on what it is you configure and how far in you're indenting, it can go and dynamically change how it's printing because it has this tree that it knows how to modify. So for the most part, as I've been creating this, a lot of this is kind of design decisions, really, of how you want to look at your Ruby code. And so for the most part, I've tried to stay consistent with RubyKaigi. I've tried to stay consistent with the overall community. I've tried to follow the rule that if it will always be idempotent, it will run on the same input, it will always generate the same output. And finally, it should never fundamentally change the meaning of your program. Now, I probably should have an asterisk there because Ruby is incredibly flexible. And because of eval and metaprogramming, technically, changing anything in your program could change the meaning of your program. So there's a happy line somewhere that we've tried to find in developing this. Just to go over, just to give a couple of examples of design decisions we've made here. The break, next, yield, and return keywords don't use parentheses. Super will sometimes get parentheses if you're overriding the arguments of the parent. There's no nested ternaries. We format numbers in very specific ways. We change between braces and do end for lambdas and multi-line. And just to give some more concrete examples, you can see it. We'll always favor aliasing with bare words. Array literals get transformed automatically in your source code, so if we can transform them. We will automatically convert things into using the shorter symbol 2proc syntax if we can. This is actually kind of interesting because technically that changes the arity of the block that's being passed in. So this became an option that you can optionally turn off if you're doing some pretty in-depth introspection here. Do end and brace blocks get converted if they can be, depending on operator precedence. Ternaries become automatic if you have simple if-elses. If you have anything complicated, it won't automatically do that transformation. Inline rescues become multi-line rescues, just to be a little more explicit. And strings. We're trying to be very careful with strings. If you have any escape sequences at all, we don't change the quotes. But if you have simple strings, we will go and change the quotes to be a little more consistent. We also, as you can see at the bottom of the slide, get rid of any kind of dirty interpolation and automatically use the pound and braces. In general, the philosophy from Prettier has been to minimize options. And really, the idea behind that is just because the more options you have, the more discussions you end up having. And oftentimes these lead to unnecessary bike shedding. So in the past, Prettier has added options to increase adoption of Prettier, which is no longer done because Prettier has already taken off and there's plenty of folks using it. When there's great demand from the community for an option, they have added those options. But that's kind of an interesting discussion because a lot of the philosophy stems from the idea that if Prettier existed when all these languages first came around, it wouldn't have been necessary to add these options because there wouldn't have been time for these communities to entrench in their ways of thinking about the right way to do something in a programming language. Because Prettier is coming in later, once these communities have already developed almost like dialects in a language, we have only added those options that truly reflect the trenches that people have fallen into. And finally, compatibility reasons with various formatters in other languages. Specific to the Ruby plugin, I provide these 6 options. They are meant to provide for the various dialects that I have seen in the community. If there is absolutely great demand for others, I will add them, but this seems to represent most of the trenches that people have fallen into. So now we get to what I feel like is kind of the most important part of this presentation. Because Prettier is embedded in an ecosystem, it's embedded in an ecosystem of other formatters. we get to take advantage of a lot of great stuff. And one of my favorite pieces of this entire thing is that you can embed parsers within other parsers. And what do I mean by that? As a concrete example, if you have a script tag within HTML, you want to both format the HTML code, but then also format the JavaScript within the script tag. So there aren't a ton of examples of this in the wild, but there are some times where it's just nice. For instance, you can embed Ruby code within other languages. If there's ever a time where you're executing Ruby code or showing Ruby code and you want it to be formatted, because Prettier can embed the Ruby parser into a larger parser, it can actually be formatted correctly. And I'll show you an example of this in just a second. Also, you can embed other languages within Ruby code itself, which can then be formatted appropriately. So for example, if we have a here doc and it says, and we know that it's using Markdown to format, and this is somewhat badly formatted Markdown, because Ruby is part of the Ruby plugin is part of this larger ecosystem of plugins, it actually knows that it has access to a Markdown formatter. And what it can do is detect that it's inside of a here doc with the correct prefix and pass it off to the Markdown formatter to get better formatting. And indeed, this is what it does today. Also, if we have embedded Ruby inside of something else, for example, like a Markdown file going back the other direction, we actually can have it go and format that appropriately. And one of the biggest benefits of having all of these things is that you can start to build other pieces onto this to really have tons of rich ecosystem of all these plugins. And so in addition to shipping the Ruby parser and the Ruby formatter, the Prettier for Ruby plugin additionally ships with support for the HAML template language. And one of the nice things there is that HAML actually has a concept called filters. And filters allow you to put other languages inside of your HAML code. For instance, one of those being Ruby. And today, it will detect that you're using a Ruby filter and actually properly format your Ruby code within that filter. So this is all part of building within this ecosystem and taking advantage of all the work of all of the other developers as well who have done stuff outside of the Ruby ecosystem to build this great formatter for Ruby code. Going forward, I'm going to be working on lots of things. Number one would be speed. There have been a lot of interesting experiments in this. The one I want to show today is a Node native plugin that will actually, instead of spawning a Ruby process, just return the Ruby objects directly into the Node process. Funny enough, this actually works great if you have enabled shared code within the Ruby installation, but not everyone has that when they've configured Ruby, so this might be a non-starter, but this is still an ongoing experiment. The other experiment that I'm looking at is replacing the Prettier printer for their nodes from the JavaScript side directly into a C library that we can call from Ruby. And this is just an excerpt from that code, and so that is an ongoing experiment as well. Finally, I'm trying to keep up with all of the latest and greatest Ruby syntax that it comes specifically in 2.7. We now support pattern matching and all of the variants therein with array patterns and constants and hash patterns and all things like that. So that's exciting new features that I'm constantly working on to stay up to date with Ruby as it goes. So if you like this presentation or you're interested in better formatting your code, I hope you can get involved and check it out. It's on GitHub. We're constantly working on new issues and pull requests, and it's a good time. And finally, try it today. We have integrations into every single major formatter that we can find. So if you would like to try it, I'm sure it will work with your workflow. And yeah, thank you very much, and thanks for watching.
Hey, my name is Ernesto Tackworker, and I'm here to talk about RubyMem, the Leaky Gems database for Bundler. Now, this is a relatively new project that helps us find dependencies in our application that are known to have problems with memory usage. If you have any questions or comments, feel free to shoot me a message on Twitter. My handle is etackworker. Now, I'm originally from Argentina, so if you hear any words that sound funny, it's because English is not my native language. If you have any questions in Spanish, the good news there is that I can help. I have been living in Philadelphia for the past 4 years with my wife, daughter, and son. I really like it here. There is a small Ruby community that I help organize. Now, due to COVID, I've been spending a lot of time at home working and taking care of my kids. Now, my daughter loves to draw, so I love drawing with her, and she really wanted me to share this drawing with you. This will explain why you'll see some drawings of my own in this presentation. Now, they're not as good as hers, but I tried my best. And one last thing about me is that I love open source. I wouldn't be here speaking if it wasn't thanks to open source projects like Ruby, Rails, and many, many more. So I try to get back to the community as much as possible. I'm one of the maintainers of Database Cleaner. You might have used that gem in the past. It helps you keep a clean state of your database between test runs. I also maintain Next Rails, which is a toolkit for your next Rails upgrade project. It helps you with things like dual booting your Rails application and finding incompatibilities with the next version of Rails. And Skunk is a project that helps you assess technical debt in your Ruby applications. It looks at all the files in the application and it tells you these are the most complex files which lack test coverage. It uses tools like RubyCritic and SimpleCov to do this. If you're interested in any of these projects, please feel free to check them out on GitHub. I'm also the founder of Ombu Labs, which is a small software development shop based in Philadelphia. We love Rails, we love Ruby, and we love working remotely, among other things. Now, if you're interested in working in challenging projects and working remotely from anywhere, feel free to check out this page. We are currently hiring, and we would love to hear from you. A couple years ago, we found ourselves working a lot on Rails upgrade projects and Ruby rescue projects. So we decided to launch a service called fastruby.io. In the work that we do with Ruby rescue projects, we end up working a lot on performance optimization, which requires us to look into the memory usage of not just our clients' code bases, but also their dependencies. A lot of the tools I'm going to talk about today, we use on our client projects on a weekly basis. And when I talk about memory issues, I'm not talking about you forgetting something and then realizing about it. I'm talking more about applications using way too much memory, so much memory that it becomes a problem. And that happens with Chrome sometimes on your Mac computers. So I'm talking about memory issues as in RAM issues. Sometimes I'll be talking about memory leaks or memory bloats. Sometimes the root cause will be in your Ruby gems. Sometimes they'll be in your application code, and sometimes they'll be in C extensions within your Ruby gems. So this can be a very tricky issue. I think it's easiest when we look at it with a story. So it is story time. A few years ago, my boss comes up to me and he's like, "Hey, can you help me with my project?" I'm like, "Sure." How can I help? Well, can you make my GIF search engine faster? And I had never heard of this project before. So I asked him, yeah, I mean, maybe you can show me what it looks like before I start working on it. And he's like, yeah, sure. Basically, you have a search box, you plug in a keyword, and you get 5 GIFs. Very simple. And I'm like, yeah, that is super simple. I wonder how I can make it better. And I say, okay, maybe I can add a simple cache to it. Behind the scenes, I see that it's a Rhoda application. It is not a Ruby on Rails application. I work a lot with Ruby on Rails, but this one in particular is a Rhoda application, which is another popular framework in Ruby. It's also a rack-based application framework, just like Rails. When I look at the search action, I see that it's using a query object. So I dig deeper. And I see that the query object has a search method which makes third-party requests to the Giphy API. And Giphy is a GIF directory. There are a lot of GIFs in Giphy. So if you think about it, this is basically a wrapper for the Giphy API. And I think, okay, I'm going to write my cache in Ruby with a hash. Simple. I work for a couple of hours and I come up with the next solution. It's a query cache constant that is a hash object. I save the values that I get from the Giphy API in this cache, and I use the keywords as values. So this guarantees that I won't contact the Giphy API more than once per keyword. So I get it code reviewed, tested, everything looks fine, and I ship it. I reach out to my boss and I say, hey, I just shipped a bunch of changes, which included my caching solution. I also bumped the version of Rhoda, REST client, and Puma, and I upgraded the Heroku stack as well. My boss is happy, the users are happy, and my boss is like, good job, Ernesto, everybody's happy. Great, I take off for the day, go home, and don't think about it anymore. The next day, I hear that users are seeing errors in production. They can't find the laser cat GIFs that they want, which is terrible. I know. And I feel awful because I'm the last one to deploy things to production. So I say, weird, I'm going to check the logs. And sure enough, when I look at the logs, I see that there are a bunch of memory usage error messages. I'm like, error R14, memory quota exceeded. What is that about? Before I can take a look, my boss pings me on Slack. Hey, I noticed this weird behavior in our production's memory graph. I check out the Heroku dashboard and I see that memory usage has increased constantly since I deployed the application. I see that 12 hours into this new deployment, we run out of memory. And yes, I confirm that looks bad. We run out of memory overnight. But I'm hesitant. I say, my code was so small, there's no way it's my code's fault. It's probably Rails' fault. But then I remember, hey, I'm not even using Rails, so maybe it's Rhoda's fault? After all, I did deploy a version bump for Rhoda. So maybe that's it. My boss, who has a few more years of experience, is like, what's more likely, that Rhoda has a memory bug or that your code has a memory bug? Well, maybe you should check the changelog for your latest deployment. And I say, Sure, good idea. I'm just going to start debugging this. And I ask myself, what tools can I use? I know that Ruby has some tools in the standard library. So I say, okay, I'm going to use object space to find out how many objects are getting instanced and kept in memory between the requests that I'm making to the application. So I add this snippet that will count all the object instances in the Ruby memory, and it will tell me which types are the most popular right now. And I start using the application with this new method, and I see that hashes and strings are growing. But I'm still not convinced about this behavior. I'm not convinced that my application code is the problem. So I'm not sure. I'm going to use Rack Mini Profiler and Memory Profiler to look into it a little bit deeper. So I add these gems to my application, and I require the libraries right before I start my application. The good news is that Rack Mini Profiler gets loaded as a Rack middleware, and Rhoda is a Rack-based framework. So with a one-liner, I can add Rack Mini Profiler to my Rhoda application. And this allows me to add parameters to the requests that I make. Like this one, if I add pp equals profile memory, I can start seeing information about the memory usage of my application. I can see the allocated memory by gem and by file, among other things. I can even see allocated objects by class. Now, I need to see the behavior of the memory across different requests and see if all the objects that I'm adding to the application are getting garbage collected or not. After a few hours of debugging this problem, I realized that my code is the root cause of the problem. And I go back to the changes that I shipped to make sure that that is where the problem is. Now it becomes obvious that the cache has limited memory space, but the queries that I receive could be infinite. People could search random keywords, and my application's memory would just fill and fill and fill to eventually run out of space. So my solution, it seems that it's causing a memory bloat. In order to fix it and to find a better solution, I'm going to revert my change and deploy. And when I do that, I notice that the memory usage in the Heroku dashboard drops dramatically. Okay, I fixed that problem. My boss is like, great, what was the root cause of the memory leak? And I explained, well, my cache could end up using infinite memory, but we only have 500 megabytes available in our Heroku dynos. And then the next question, of course, is why did you take so long to fix it? And I try to explain, I shipped so many changes that I didn't know which one caused the problem. I didn't know whether the leak was in my application code or in my dependencies. All right, so story time is over. Let's see what lessons we learned with this. First one is anyone can introduce a memory bloat or a memory leak. It can be you, it can be one of your teammates, or it can be a well-intentioned open source developer who is just trying to make their library better. It is so easy to introduce these problems to your application, but it is not as easy to find the root cause of the problems. It gets even harder if you're constantly deploying changes to your application and you can't let your application instances run over time to see how they behave with memory usage. The good news is that there are great profiling tools in Ruby. I mentioned just two, but I know that there are many more, like Flame Graph, derailed benchmarks, and many, many more. So after this particular experience, we asked ourselves this question. If only there was a way to quickly answer this question. Is it my code or is it one of my dependencies that is leaking memory? And that's what Bundler Leak set out to fix. To answer that question, are we using any dependencies, any Ruby gems that are known to have leaked memory in the past? And in order to answer that question, you can quickly install the library in your gem file. After you do that, you can run bundle leak, and it will tell you whether there are dependencies that are known to be leaking memory or not. So if it doesn't find anything, you can say, neat, none of my dependencies are known to be leaking memory. So I feel confident that the root cause is within my application code. I'm going to debug my application code. On the other hand, if you run bundle leak and there is an issue, it will report it like this. It will tell you net HTTP persistent 300 has a problem. And it will link you to the source of the report of the memory leak. Then you can take a look in your gem file and see that, yes, you are explicitly trying to use that version in your application. And you might ask yourself, do we need to use that particular version, or can we upgrade to version 301? Maybe you can just bump that dependency. So you do just that. You change the dependency declaration to use 301 and you bundle update. After you do that, you run bundle leak again, and great. Now you see that there are no dependencies that will cause any problems. The awesome thing about this is that in a few minutes, you fixed a problem with memory leaks in your application. There was someone who reported that leak to net HTTP persistent. There's someone who took the time, probably hours of their time, to patch that problem. So with bundle leak, what you can do is quickly use that information to save time in your day-to-day. And you can say, okay, no more leaky dependencies. Now let's check again. Are we still leaking memory? If so, then you probably want to look at your application code and see what you're doing to cause problems with your memory. Here are a few details about the implementation we did with this project. First of all, this project was inspired by Sergey Alexeyev's project called Leaky Gems. He started a project that would track all those reports of all the gems that had problems with memory usage. It was basically a README that people could submit pull requests to. What we did is we turned this easy format into a machine readable format in order to build a command around it. So we turned that particular project into the Ruby Mem Advisory DB. And you can check it out on GitHub. There is a directory that has every single gem that is known to have had an issue with memory leaks. And you'll see that our report looks like this. It has the gem name, the date it was reported, it has the versions that are affected, and it has the versions that have been patched. So it provides a clear path for you to fix this problem. Another thing is that Bundler Leak is a fork of Bundler Audit. If you're not familiar with Bundler Audit, well, It is a really cool tool that you can use to find problems related to security vulnerabilities. Bundle Audit will tell you whether you're using a vulnerable version of a Ruby gem or not. And it will tell you where you can find more information about it. If we look at them side by side, we can see that Bundler Audit and Bundler Leak are very, very similar. In order to run Bundle Audit, you just run bundle-audit. To run Bundler Leak, you just run Bundle Leak. So just like Bundler Audit has the RubySec Advisory DB, we have the RubyMem Advisory DB. So they're very, very similar. And one note about this is that RubySec and RubyMem are not connected at all. RubyMem just forked RubySec and used the same idea, but as a source of data, it used known leaky gems as the source of data. So why isn't RubyMem part of RubySec? Well, the truth is that not all memory leaks are security vulnerabilities. Some might be, and maybe it's a good idea to integrate both projects around them, but many of them are not actually a security issue. Now, there are a couple things that we want to do with RubyMem and Bundler Leak. We've noticed that the more reports we get, the more value we can provide to the community. And we know that there are many, many libraries out there that are known to have memory issues and we're not tracking yet. So what you can do is maybe go back and check the leaky gem that caused you a big headache maybe a few months ago, and check whether we are tracking it with the RubyMem Advisory DB. If the leak has been patched, or if the leak has not been patched, we recommend that you go to rubymem.com and submit it privately. Sometimes a memory problem could be a security issue, so we don't want to disclose it unless it's been patched. If the gem has been patched and the patch has been available for weeks or months, feel free to submit an issue to our project in GitHub. And finally, we are looking for contributors and co-maintainers. So if you're interested in helping out with this project, the best thing you can do is run Bundle Leak in your projects and see if they work or if there are unexpected behaviors that could be a bug. Next time you ask yourself this question, is it my code or is it a dependency? You can save yourself a lot of time. Next time you need to go down the rabbit hole, I recommend strongly that you use Bundle Leak first. And then you can pick the rabbit hole. You can go down the dependencies rabbit hole or the application rabbit hole. And hopefully it will save you a lot of time. If you're interested in this project, it's on GitHub. And if you have any questions, feel free to shoot me a message on Twitter. I'd like to give thanks to Sergey Alexev for creating the project that started it all, to Nate Berkopek for suggesting this idea for this really cool tool, and to my coworker, Luis Sagastume, for implementing these projects with me. Thank you very much for your time. I hope that you will take this tool and put it in your tool belt so that it can help you in your next performance optimization journey. Thank you. If you're interested in any more resources, feel free to check out these pages.
Hello and welcome to my talk running Rack and Rails faster with Truffle Ruby. My name is Benoit Dalloz and I'm the project lead of Truffle Ruby. Truffle Ruby, if you don't know yet, is a high-performance Ruby implementation by Oracle Labs. It uses the GraalVM JIT compiler to achieve its good performance. It targets full compatibility with Ruby 2.6, including the C extension. And it's open source and on GitHub. There are two ways you can run Truffle Ruby, like two VMs. So you can run it on the JVM, and then the main advantage is you can interoperate with Java conveniently. And you can run it in native mode, which is the default, where the Truffle Ruby interpreter and the Graal compiler are compiled ahead of time to a native executable. So this is like the end result is a bit like MRI, like you have one executable with everything in it. And this provides faster startup, faster warm-up, and lower footprint. And the reason is basically you have a VM specialized for Truffle Ruby with nothing else. Doesn't need to be as generic as a JVM, doesn't need to load classes dynamically. No, it's just like running Truffle Ruby, and that's what it's specialized for. In terms of compatibility,
Hi, welcome to RubyKaigi Takeout 2020. I hope you're enjoying all the content. Today, I will be reflecting on Ruby reflection for rendering RBIs. My name is Ufuk Kayserlioğlu, and I'm a production engineering manager on the Ruby infrastructure team at Shopify. So a quick intro to the concept. When I joined Shopify at the beginning of 2019, the first project that I joined was the adoption of Sorbet on our code base. So for those of you who don't know, Sorbet is a static type checker built by the fine people at Stripe. And on the project that I was on, we were trying to adopt gradual typing using Sorbet on our Rails monolith. As we were working on that adoption, we quickly came to the realization that we had a problem with Ruby gems. And the reason why we had a problem was that Sorbet doesn't look into your gem dependencies, so it has no way of knowing what's been exported out of those gems. It only type checks your user code. But that's a problem because the cost of entry for the gradual typing adoption with Sorbet is for all references to constants in your code to resolve. So if you're referring to a constant or a module in your code, then Sorbet needs to know what that constant is. But unfortunately, because it doesn't know the constants coming from gems, it has no visibility into those, so it errors out. Quick example for this, which is a contrived code, but it's totally possible that someone has some code like this in their code base. So if you have a myCLI class that subclasses from Thor and calls the class option method, and if you try to type check this with Sorbet, Sorbet will be thinking, what is Thor? Where did that come from? I don't know any Thor class. And also who defines class option as a method? And also what parameters does class option accept? Because without knowing that, how am I supposed to type check if the parameter that was supplied, in this case a symbol, is the correct type or not? So because of that, if you try to type check this file using Sorbet, you will get type errors. The way to solve that, which was a concept developed by the Stripe team as they were working on Sorbet, was the concept of Ruby interface files. So Ruby interface files are actually Ruby files without all the implementation detail. So here, I will show you an example of what Thor.rbi might look like. So it again declares the class Thor, and it declares a Thor class methods module, which has a class option method with 2 parameters, and then the Thor class extends from that. So if you write this RBI file by hand and then give it to Sorbet as you're type checking your CLI Ruby file that I've shown you before, then Sorbet will know what Thor is and where the class option method is coming from and what the parameters are. So it will be able to type check this. So this Ruby interface file is like a C header file almost. So if you write this by hand and supply it to Sorbet, then it will be able to type check the whole thing. But this is super hard to do for all the gems that we have a dependency on, and let alone to keep those maintained. In our core, in our monolith, in our code base, we have a dependency on more than 400 gems, and it would be a nightmare to keep those all updated. So can we automate this? And the answer is yes, you can using Ruby reflection, so that's what I'll be talking about today. So reflection as a concept is the ability of a program to examine or manipulate the type, properties, methods, or values of an object at runtime. And we actually do that a lot in our Ruby programs. You might not be aware of it, but every time you call define method or every time you call alias method, you're actually doing reflection. So we'll just be using the introspection part of reflection to read what these things are and not change them to get all the information that we want. Before we begin, I want to remind you that in Ruby, everything is actually a constant. So we're used to declaring classes using the class keyword or the module keyword. So here, the code on the right on top declares a superclass, and then declares a foo class that subclasses from super, and then declares a bar module inside the foo class. But that's exactly the same code as defining a super constant and then assigning the value class.new to it. Class.new creates a new instance of a class. So it creates a new class. And then by assigning it to the super constant, you give it a name. So that's exactly the same thing as doing class super and end. And similarly, if you give an argument to class new, that argument becomes the superclass. And then there's a similar method. So there's a similar class, which is module. And if you call module.new, that creates a new module. Notice that super and foo are constants defined under object because everything lives under object in Ruby. And bar is a constant that lives under the foo constant. So everything in Ruby is actually a constant that lives either in object or under another constant. So I'll be talking about constants throughout this presentation. So this is what you should understand. So we started with this store.rb. So this is, again, an example of what the actual Thor code might look like, but I stripped it down to its essentials so that we can look at it. And what we're trying to do is to take this store.rb and just using Ruby reflection and no extra outside input to be able to convert that into the corresponding RBI file. So in order to do that, we need to somehow understand the shape of what's being declared in this Ruby file in the store RB, and to grab the parts of it, to grab the name of the top level class, and then the name of the module that's defined inside it, and like all the methods that are defined there, and all the extends and the includes, and then to generate the RBI file. Okay, let's get started. So first of all, we need a way to grab constant references given their name. And that works by calling what we can first call const defined with a question mark and then give it a name. And then that tells us if that constant is defined or not in the given context. In this case, the context is object. And then if we say ask object, is this constant defined, and give it Thor, then it says yes, that constant is defined. Oh, okay, now that we know it's defined, we can actually get a reference to that constant. So that's the const get method. And if we call the const get method, we can assign the return result to a local variable. Note this is like lowercase Thor, so it's a local variable, but it holds a reference to the Thor class. So we can get a reference to the Thor class just using its name. Now that we have a reference, we can call Thor.name, and that will give us as a string the name Thor. So we get our first piece of information, the name of the top level class. So we can use that in our RBI generator. Basically, we're trying to piece together strings to generate an output. But we can do even one better. We can say Thor.superclass, and that gives us object. So now this might be surprising because we didn't declare any superclass for Thor class. But in Ruby, basically, if you don't declare an explicit superclass, the implicit superclass is always object. So that's the piece of information that we get returned. We can also try to get like all the includes and the extends defined in one scope. So we'll try to get those for the Thor class. So all we have to do is to say Thor.included modules. In this case, that returns an empty array because there are no modules that are included in the Thor class. Can we get the list of extends? Yes, we can. All we need to do is to access Thor's singleton class and then ask for the included modules in the singleton class. I won't go into what a singleton class is, but it's basically the class that the Thor class is an instance of. So if we do that, we get Thor class methods. Okay, that's good. But we also get kernel because kernel is included in the singleton class of Thor's superclass, which is object. Object brings in kernel. So we want to get rid of that. and we don't want any outside input into this whole process. So what we can do is we can try to get Thor singleton class included modules, and then subtract from that Thor's superclass singleton class included modules, and which will be kernel. So we would have subtracted kernel, and then we just get Thor class methods. And that gives us the extend that we need. So let's try to grab the subconstants of a constant, all the constants that are defined within the constant that we're looking at. So we can do Thor.constants. That will give us the names of all the constants that are defined inside the Thor class. And in this case, that name, there's only one, and that name is class methods. But that's just the name of it. We want to get access to a reference to that class methods. So what we can do, we know that const get works that way. So if we call const get on Thor and give it that name, so if we do Thor.const get and then give it Thor constants first, then we get a reference to the Thor class methods module, which gives us that module definition there. And we can ask for the name of it to grab the name and to generate it in our RBI. We can also get method names of a constant. So that's also simple. If we do methods and then we call now CM holds a reference to the class methods. And if we call instance methods on CM, that gives us an array of all the instance method names that are defined by class methods. And the fact that I supplied false there means just give me all the methods that are defined by class methods itself. Ignore all the ancestors of class methods. Okay, so we get the name of that method as well. Let's see if we can, again, get an instance of that method too. And well, we actually can, because everything in Ruby is an object. So we can say, we can call cm.instance method and give it the name of the instance method that we want an object for, a reference for. And in this case, we're giving it class option, and that returns an unbound method that represents the class option method in Thor class methods module. Okay, so now we have an object that represents the class option method. Now, can we get the parameters of this method? Sure, we can. If on that method, we call dot parameters, that returns an array of tuples. For each tuple, the first entry is the type of the parameter and the second entry is the name. So in this case, that's saying class option method has two parameters. The first one is a required parameter with the name, and the second parameter is an optional parameter with the name options. An optional parameter means it's got a default value, so you don't have to supply it when calling. A required parameter means it doesn't have a default, so you always have to supply it. So we can also get the parameter names and the different types of parameters if it has a default value or not. We can do even more. We can get the location of a method by calling method.sourceLocation, and that returns again a tuple, and the first entry being the file name where that method is defined. The second entry is the line number in that file where the method is defined. So this is useful if you want to check if this method is actually defined in this gem, or that method is defined on this module, but from another gem. So you can actually test to see if it's inside the gem folder or not. And the observant people in the audience will say, wait, you said this is going to be totally automated. You said there wasn't going to be any external inputs into the whole process, but how did we get the initial Thor symbol, right? We supplied the initial Thor name to start this whole chain, but where did that come from? This is a bootstrapping question, and it's a really legitimate question. And the way we found to resolve that was to bootstrap using sorbet itself. So sorbet, being a static type checker, needs to understand your Ruby code. Understanding Ruby code means it needs to be able to parse it and make sense of it. So you can actually ask sorbet to print more than just static type error output. In this case, we're asking Sorbet to print the symbol table of how it sees the symbols in the Thor.rb represented in its own language. And this is like really complex output because it's like very specific to Sorbet. But you can actually see that Sorbet has seen a class named Thor that's being declared in that Ruby file. And it also sees the module Thor class methods. And it actually even sees the method and the arguments to that method, etc. So this actually, we do this to grab all the top level class and module names, and then we use those names to bootstrap this process of reflection to get all the subconstants and to walk down the hierarchy and to generate the RBI. Now you might be asking, yes, but like if you have this ability to find all the classes and the modules in the code base using static analysis, why don't you just do that? Why do you have to do runtime reflection? And the answer to that is because Ruby is a dynamic language. Because Ruby is a dynamic language, there's lots of gems that do a lot of stuff at runtime, right? Creating methods, like creating new classes or new modules at runtime. And if you just use static analysis, you miss those. But if you do runtime reflection, all the code is executed and in memory, so you can actually just walk through that memory contents and all the methods would be defined, all the classes would be defined, and you will have access to a richer representation of the gem. There are a few pitfalls to doing runtime reflection, and I'll just quickly talk about those. So the first is types that lie. So classes or modules that explicitly lie. So in this example, we have a class foo that subclasses from standard error, and it declares two class methods, name and superclass. So what happens is if you call foo.name, what's returned is bar as a string. And if you call foo.superclass, it returns string. But we expect the result of the first thing to be foo as a string, and the result of the second thing to be standard error because that's the superclass, right? So this type is obviously lying. The solution is to call the base method. The base method being the method that actually defines the name and their superclass initially before foo overrode those methods. So the name method is defined by module. And we can get an unbound method that represents that name method like we've seen earlier. So if we ask module, give us the instance method with the name, and it gives us an unbound method. So unbound method, we can't call this unbound method because there's nothing to call it on, but we can bind it to something so that we can call it on that thing. So what we do is we call module.instance method name, and then we bind it to foo, and then we call it, and that will give us the string foo, the real name of the foo class. And similarly, if we get the superclass method on class, and then bind it to foo, and then call it, it gives us the correct superclass standard error. This is made even easier in 2.7 and above versions of Ruby, which introduces a new bind call method. So you don't have to call bind and call separately. So that saves a few keystrokes, but it's also a little bit more performance. So you'd rather use it if you're working with a code base that works on 2.7 and above. Another pitfall you might be running into is this private superclass. So if a class has a superclass, that's a private class, and if we generated an RBI file with that superclass, then Sorbet will say, oh, like, you know, you'd say this is the superclass, but this is a private class, so, you know, I don't know what this is, and it will error out. So we have to be careful with this. So an example situation here is a module mygem that declares a superclass, a class named super, and then says it's a private constant, and then declares a class foo that subclasses from super. So if you say mygem foo.superclass, you get access to like a reference to mygem super. There's nothing wrong with that because that's the superclass. But if you try to access mygem super, then actually you will get a name error because it's a private constant. Mygem is hiding it from the outside world. So the solution for this is actually easy. You check for private. So there's like, you do some evaling. If we define this public module question mark method that accepts a class, we can eval that class, which if the class is referring to a private constant, will raise a name error. And if we catch the name error, we can return false, knowing that it's a private module. And then if we call that method, and if it's false, then we just skip generating that superclass for the class foo. Another pitfall, and this is like one of my favorites, and this is adapted from an actual gem code, but like simplified. So there is a few gems out there that actually use this technique. So this is a class that ends up being its own class. So here it's very simple. You define the class foo and subclass it from standard error, but then you create a new class using class.new that subclasses from foo, but then you assign the result of that to the foo constant by overwriting that name. So what happens is, if you ask foo, what is your superclass? It says my superclass is foo. But you say that's not possible. This class cannot have itself as its superclass. So you check the object IDs. Well, they're different, obviously, because they're different instances. They're just names happen to be the same, and they're not even equal to each other. So the solution here is their names are different. Their names are the same. So they both have the name foo. So if you compare the names and if they're the same, then you can again skip generating that superclass. There's a worse version of this, which I call insidious class hierarchies. So in this case, if you define a class bar and define a class foo that subclasses from bar, and then you overwrite bar by aliasing it to foo, here foo's superclass becomes bar. Foo's superclass's name is the string bar, all fine. But if you ask bar, who are you? It says I'm foo. And if you ask bar, what's your name? It says my name is the foo string. And even worse, in this case, the name trick doesn't work because the name of the foo class and the name of foo's superclass are actually the same, are actually different, sorry. So we can't even skip it. So the solution is to get a fresh reference to the objects from their names. So we get a fresh reference to foo using foo's name and using const get, and we get a fresh reference to foo's superclass using its name and using const get. And in this case, the names will be the same because the bar name refers to foo, and the name of that will be foo as well. So this is the solution. And as for a bonus content, working on our code base, I realized that if you, our code base has a dependency on parser and Rubocop and the OJ gem. And if you require Rubocop first and OJ second, everything works fine. But if you required OJ first and then Rubocop second, you got a name error with an uninitialized constant. Ultimately, I dug this down into a bug in OJ. And what OJ was trying to do was it was trying to remove the constant, basically delete the constant JSON parser, but it was calling remove const on the top level object. So it was actually removing the top level parser constant by mistake. So this was a one-line change that resolved that error in the OJ gem, but it's surprising what things you can discover as you're working with this runtime reflection thing. So in summary, Ruby has a very nice object-oriented reflection API, but the dynamic nature of Ruby makes reflection hard. You need to resort to lots of tricks to get it right. But the nice news is generating Ruby interface files for random gems is now a solved problem because we open sourced the result of all our work as the Tapioca gem. So you can go to this GitHub repo, take a look at the code base, and if you're working with Sorbet, you can start using it in your code base as well. Thank you. You can always reach me if you have questions or comments on Twitter or GitHub using the Paracycle handle. It was a pleasure speaking at RubyKaigi Takeout 2020. See you around.
Hey everyone, welcome to my RubyKaigi 2020 Takeout Edition talk. My name is Vladimir, and today I'm gonna answer some questions regarding transpiling Ruby. Hey everyone, welcome to my RubyKaigi 2020 Takeout Edition talk. My name is Vladimir, and today I'm going to answer some questions regarding transpiling Ruby. So, Ruby, that's our favorite language, and we're going to talk about it today, and its present, past, and future. And we're also going to talk about such a specific tool as a transpiler. So, what is a transpiler? Transpiler is a program that translates a source code from a language to another language at the same level of abstraction. And it's usually called a source-to-source compiler because it's actually a specific case of compilers, and the input and output source code is usually of the same language. One of the most popular transpiler is a Babel from the JavaScript world. It's due to Babel, I think the word transpiler became popular. Yet another transpiler from the front-end world is PostCSS. It's a transforming tool for CSS, which also allows you to use modern syntax in older browsers. But how on earth all of this relates to Ruby? Why we talking about such a hack as transpiling for preferably server-side language? Why do we need transpiling for Ruby? Let's take a look at the Ruby future, Ruby free. So currently Ruby free working version number is 2.8. So I'm going to use this version in the talk. And it's going to be released in a few months. So Ruby is evolving fast nowadays. Recent release 2.7 brought some new features, including new syntax, and the upcoming release will add even more new syntax features. Let's take a look at the example Ruby 2.8 program. Doesn't it look unfamiliar to you? We have here pattern matching. Okay, this is pretty old. It's almost 1 year old. You know about it. Maybe you even used it. But another one, endless method definition. I doubt a lot of you using it in everyday life. And also we have here right word assignment. Like it's just, assignment, but in a different direction. Pretty cool. And it's also coming in the next version. But it's kind of hard to use these features today because you need either an Edge Ruby running on your system, or you need to build it from source or whatever. So you definitely don't use these features in production, right? And maybe you would like to use them in the current version which you use, your current Ruby. How to do that? Well, with the help of transpilers. And we have a transpiler for Ruby, and that was one of the reasons I started working on this project. Yes, I'm working on Ruby Next for about a year, and the main reason for that is to make it possible to use modern syntax features with older Ruby. And today I'm going to talk about why I decided to build it and how does it work. So what is Ruby Next in a simplest way to demonstrate how it works before we gonna talk about whys and hows. So assume that you have an older Ruby version, say 2.5, and you want to run the following code with pattern matching in it. And if you don't have a magic Ruby Next switch, it will just raise an exception, but with Ruby Next, it works. That's what transpiler does. That's what transpiler does for you. So it makes it possible to use modern Ruby, to write modern Ruby today, to write modern Ruby yesterday as well. So my name is Vladimir, and let me first introduce myself, just a quick bit. So you can find me on GitHub under the Falcon nickname. There you can find my open source projects and information about my social networks, writings, whatever. I'm working for a company called Evil Martians. We're a distributed team of senior developers, front end and back end and whatever end, designers and DevOps engineers spread all over the world with 4 bases in 3 countries, including Japan, USA, and Russia. And we helping big companies and small startups to make the idea live or help them to deal with performance bottlenecks, to do some crazy stuff with their idea, to implement their ideas or whatever. So we just helping other people to do their work to make their projects better. And of course, a part of our work is working on open source tools. Open source tools we use in our everyday life, and we trying to make them better, trying to build new tools to help us and to help the community we love, like Ruby, front end, Golang, whatever. And we write about everything we do in our blog, so check it out. Most of our articles, especially popular ones, translated into Japanese and Chinese and sometimes other languages, so check them out. That's pretty much everything for the introduction of myself and my company. Let's switch to the main topic and talk about why we want to transpile Ruby. I already mentioned the problem of backporting, so the desire to use new features, upcoming features, before they're released with older versions for different reasons. Let's take a look first at some raw stats from Ruby gems. As you can see, not a lot of people or machines are using Edge Ruby, latest Ruby, even the previous version. So the majority of Ruby users, being humans or robots, are still running older versions, and they cannot use new features. And what does it mean for them? Okay, they probably are okay with using older syntax, but for me personally, as a gem author, I'm maintaining a couple dozen of gems. That means that I cannot just drop support for older Rubies, and I have to support at least those Rubies officially supported. And as of today, it's 2.5 and above. And I cannot use better matching with 2.5, right? And most gem offers cannot do that. So they should stick to the older version. And even if in the case someone decides to, build a new gem and support only 2.7 and above, there's a high chance that people come and ask for not doing that. Please avoid pattern matching, but allow us use your gem. And that's particular story with Hanami API gem is very interesting, not because of this request, but because it reveals another side of the problem with new features, new syntax. And this problem is other Rubies, alternative Rubies, but I don't like the word alternative, they are just different Rubies. So we have MRI as a baseline implementation, and we have JRuby, and we have Truffle Ruby, and more. But let's even talking about 3 of them, those 3, we can say that they're not kind of compatible in terms of new syntax features, and we need to wait while other Ruby's maintainers will add support for MRI features. Currently, JRuby supports 2.6, Truffle Ruby as well. And speaking about other Rubies, we also have mRuby, which has limited support for 2.7 features, but no pattern matching, for example. And Opal, RubyMotion, Artichoke. I don't know exactly about their compatibility, but I think they do not support pattern matching as well. So these Rubies won't be able to use new features in the nearest time. We can help them by adding transpiling to their toolchain, toolblade. So this is not the only 2 whys I'm going to talk about today, but let's leave the last one for the end of the talk. and switch to the next question, how to transpile Ruby. Remember, I told in the very beginning that transpiler is a source-to-source compiler, and generally compilers work the following way. First, we parse the source code into some intermediate representation, and usually it's an abstract syntax tree. Then we do some analysis and optimizations, and finally generate a target code, or target, or whatever it could be, instruction sequence or whatever. So in case of transpiler, we parse source code, we optimize it, analyze, and we generate a new source code. So usually, in an abstract world of transpilers, we do this by modifying the abstract syntax tree and generating a new source code from this abstract syntax tree. So we generating a code from a tree, a new source code. That's how we can do the correct transpiling. And let's talk about the first step of the transpiling process and generating an AST from source code. How can we do this in Ruby? So in Ruby we have 3 popular ways of doing this. First, two Reaper and RubyVM abstract syntax tree are built into Ruby. They're a bit different, but they both allow you to get some intermediate representation of the source code, not just a string, right? Which could be used to manipulate, to modify, and regenerate source code from that in the end. And the last one, parser, is a standalone gem, and it differs in many ways from the first two. And let's skip the disadvantages of the first two and just focus on parser's advantages and the reasons why I chose parser for this first step for generating an abstract syntax tree from Ruby source code. So parser is written in pure Ruby, so just a Ruby gem. That's great because it has few dependencies and it could be used with any Ruby version. So it's version independent. You can parse Ruby 2.7 source code with parser by running Ruby 2.5, for example. You don't need to have a recent Ruby to parse the recent source code. And also parser is used in many syntax and static analysis libraries, such as, for example, RubyKaigi. So we know that this gem, this parser, works good enough, at least good enough. And finally, the last but not least, parser includes rewriting support. And that's also a great benefit because rewriting in parser allows you to change the source code in place and without modifying everything else. The problem with the general approach of generating a source code from the AST has some disadvantages. You can lose style information, layout information like spaces, new lines, brackets, whatever. It's hard to keep track of them in the abstract syntax tree. They are not a part of abstract syntax tree by default. But parser provides a different way of doing this, so you can change the code in place. And that's another reason why I chose parser. And let's take a look at the simplified source code for the transpile method. So the whole idea of transpiling is built on top of the rewriters concept. So rewriter is a module or class responsible for a particular feature. So for example, we have pattern matching, so we have pattern matching rewriter. We have numbered parameters, we have numbered parameters rewriter. So every rewriter is responsible for a single feature, and what it does is analyze the AST and applies the required transformations to the original source code to generate a new source code. So as many rewriters we have, as many times we transform the source code before it's finally completely transpiled. And here's an example of rewriter code. So this is arguments forwarding rewriter. Parser provides an API to write rewriters by defining callback functions for different node types. So abstract node types. For example, forward args node is part of the method definition with argument forwarding. This is three dots part. And send node is a method call node, representing method call. And we can take a look at the arguments of the method code. If it has forwarded args, we can do the transformation. In this case, we just replace three dots with named arguments, rest and block arguments. And that works because that even doesn't suffer from the keyword argument split, a recent problem, because in Ruby 2.7 and above, we still use the built-in mechanism. We do not need to transpile code. We use the original one. And all the Rubies work the same way with this kind of substitution. And that's what makes this approach great, because it solved one of the biggest problems of 2.7 and probably 3.0 as well. So RubyNext transpiling is a bit different, as I already said, because we do not regenerate the source code from the new AST. We do not modify the AST. We use AST to rewrite the source code in place. And sometimes we unparse bits of AST, for example, with better matching, but that's a longer story. Let's take a quick look at the example of transpiling. So assume we have this FizzBuzz implementation with pattern matching, very concise, very elegant, very readable. That's why pattern matching is cool, right? Because it allows us to write such elegant code. If we decided to transpile it by hand, like just sit and write the similar source code for Ruby 2.5, it could be something like this. It still looks pretty good and readable, whatever. Unfortunately, I don't know, transpilers, general transpilers, programs are not so smart to write such beautiful code, and pattern matching is not that simple as you might think. And transpiled code usually looks like this for such complex features. This is transpiled code with RubyNext. And you can see it has a lot of local variables, some kind of checks or whatever. The reason here is that we need to be compatible with the original code, and the pattern matching is much more complex than it might seem. So that's why transpiled code is looking more, cumbersome than the transpiled by hand. But we just shouldn't think about it. Transpiled code is hidden from the user. It's for machines. It's just for your Ruby VM to execute. For humans, for people reading your code, they can see the original pattern matching implementation. And that's the power of transpiling. We can use our kind of new syntax which provides better expressiveness, and let our older machines to run this ugly code. That's where transpile could be useful. But let's take a look at the intermediate step, analyzing and optimizing. As you might notice, the pattern matching code, transpiled pattern matching code, is huge and it has a lot of checks or whatever. That's because pattern matching is kind of, big feature, and the implementation of rewriter contains about 1,000 lines of codes. And most of this line of code are not dedicated to the logic, but to optimizations. It turned out, so I was working on pattern matching rewriter by kind of a reverse engineering the implementation from Ruby by using RubySpec and RubyTest just to make them pass. And I also added a bunch of optimizations to this code, just without looking at the original source code. And it turned out that transpiled code became faster than the native one. That surprised me in the very beginning, because it's not something you expect from the transpiler, how this huge ugly code could be faster than the original one. But yeah, it could, because I did some optimizations and I started to thinking about, well, let's take a look at the Ruby source code and Ruby C code, VM code, and see how this could be applied to Ruby, back to Ruby. And I started backporting these optimizations to Ruby. And I realized that Transpiler is not only a tool for developers, right, to make their life easier. That's also a research kind of tool which helps us to make our VM better, because you can, experiment with optimizations using Ruby, because I'm more familiar with Ruby than with C, so it's much easier for me to optimize code written in Ruby. So what I did, and then we can try to backport this back to C and make the next Ruby version faster, better. That's where Transpiler is useful. That's why I continue working on this even if the community doesn't want to use this tool. But let's talk about other hows. How to integrate Transpiler into interpreted language? That's a good question, because, unlike front-end development, we do not have build tools, we don't have backpackers or whatever, so we just run our code and that's it. How to transpile it? Where should we do this? Depending on the use case, that could be release time, transpilation, or runtime. And that's how RubyNext works. So both of these use cases use two features of Ruby, two constants of Ruby, load path and loaded features. It turned out that we can manipulate these constants to make require mechanism of Ruby work the way we want it to work, to make it load, like, for example, transpiled files instead of originals for a particular version. That's what we use for gems. The idea of using RubyNext with gems is that you put transpiled files to releases, to packages, to gem files, archives, by running nextify command. And in your code, you just add this short snippet, like setup gem load path. And this code manipulates the load path. Load path is used to resolve the absolute path to the feature you want to load with require statement. And it's just scanned from sequentially from the first item to the last item. And as soon as Ruby finds the matching feature under the path from the load path, it loads this code and marks this file as loaded, and that's it. So how can we load transpiled file instead of the original one? We can just add a load specific path to the load path to load a specific version. That's how this works. And that means that you don't need to load transpiled code for all Ruby versions. They only load it if they're required. That's the idea. The users of the modern Ruby versions will not use transpiled files, but users of the old Rubies will still be able to use your library because of the presence of the transpiled files. That's cool, I think. Runtime transpiling use a lot of hackery, especially kernel require, which is okay, scary, but we can do that pretty good and pretty easy. The main idea here is that we hijack require, we resolve the feature path, we transpile the file, and we use loaded features array to keep track of this transpiled files, the same way as Ruby. So this kind of the re-implementation of require and pure Ruby. Finally, let's talk about compilable Rubies, like Rubies which have build phase, like mruby, for example. With mruby, we do kind of a similar thing to all other transpilers. We transpile source files before the final compiling, like that's our first step. And then we do some target files manipulation, similar to the load path manipulation. Let's take a look at the source code. So I'm usually compiling mruby projects using rake compile tasks. So adding transpiling to this process is as easy as adding a required our rake task to be run before compile. And this step is specific to Ruby mruby specification. Source code, I'm not going to talking about it a lot, so if you're using mruby, you can take a look and grab this source code to see what it's doing. Let's switch to the final part of the talk and back to the whys and talk about the evolution. So how transpiling could help us make Ruby better. Recent Ruby versions have added a bunch of experimental features. So we started to add more and more experimental features, but we need an experiment. What does mean experimental feature, right? So we need a way for users to give it a try, to taste it before marking this feature as stable or whatever, or reverting it back. And that's where transpilers could help us to make this better and faster than just, releasing a feature in a major release, marking it experimental, and waiting for the next major release to decide whether it should be unmarked or removed or whatever, and probably left experimental for 1 more year. That's a long cycle. We can do this faster and easier. For example, with the help of transpiler. Let's take a look at a particular feature example. Hash shorthand. This is a controversial feature. It has been proposed a couple of times, but it hasn't been accepted all of the times. But not kind of a never again, never propose it again, it will be rejected anyway. Maths is open to our opinion, but how can we share our opinion if we cannot use this feature? If it hasn't been merged as experimental, it hasn't been implemented anywhere. That's an interesting case. Maths is waiting for our opinion, but we really cannot share our opinion because we cannot use this feature, and that's where transpiler comes handy, because we can implement this feature in transpiler, and that's I'm proudly announcing as a major feature of RubyNext 0.10, which has been released just today, I think. So you can use this feature today with transpiler. You can add it to your library or your application, and you can go back to Ruby Backtracker and provide your feedback based on your real life usage. And that's what could make Ruby core team decide on whether we need it or not. Maybe we don't need it. Maybe your feedback is going to be, oh no, I tried it and it made it much worse. It doesn't matter what's going to be the result, but we need more feedback. We need more experiments. And that's when transpiler becomes a tool for moving Ruby forward. And that's what we can do together. So share your opinion. Let's make feature Ruby together. Try RubyNext. And that's it for today. Thank you very much.
Hello everyone. Today I am online to talk to you about mRuby machine. Let me introduce myself. I am Hasumi from Matsue. I love sake, coffee, curry, and soba. I usually write Rails application and I am sometimes known as a Micron cop. Anyway, please check my Twitter account because I will trade some additional information on Twitter while this video is being streamed. This is our company, Monster Lab. We are a worldwide development firm including Matsue. Please let me know if you are interested in working with us. Okay, let's start. Chapter 1. Background of my project. According to the FAQ page of MicroPython, generally, we keep minimal of configuration of MicroPython under 80K of ARM thumbnail code, which includes compiler and interactive prompt. That means a Cortex-M microcontroller with 128 KB of flash, which means ROM, can host a minimal version together with some hardware drivers. Regarding RAM usage, 8 KB is minimal amount to run simple scripts. As Python is interpreted high-level language, the more memory you have, the more capable applications you can run. The reference MicroPython board, PyBoard, which has 128 KB of RAM. On the other hand, at our end, flashing mRuby application into 128 KB ROM and running it on 128 KB RAM are apparently both difficult. mRuby-C is a smaller implementation of mRuby virtual machine, though it doesn't have a Ruby compiler, so you have to compile the Ruby script into VM code before embedding. I admit to say, MicroPython is really strong, but I don't give up. Let's make something that doesn't exist yet. It will be a small mRuby compiler. By the way, our target microcontroller is PSOC5LP, which has ARM processor, 64 KB RAM, and 256 KB ROM. I think it will be comparable enough if Ruby compiler runs on the microcontroller. Now, I will show you a quick demonstration. You can see the PSOC on the left window. Right window is a terminal emulator connected to PSOC with serial cable. I'm starting PSOC. Then type some Ruby code such as enter. Hey, hello world. Nice to meet you. Then I will make an instance of LED class, like then class of LED is, of course it is LED. Now I can turn on the LED like this. Look at the PSOC. Yay. And I can also turn it off. Congratulations, you have just seen that an mRuby compiler and a virtual machine run together on PSOC. Chapter 2. Now we're gonna take a look at terms and tools. mruby is mruby, as you know. mrbc is a command line tool of mruby compiler. It's a part of mruby. mruby/c is yet another mruby which is smaller than the original mruby. As I said before, mruby-c is just a virtual machine and doesn't contain mruby compiler. So we usually use mrbc to make VM code for mruby-c. There are very new words on this page. mmrbc is the key product of today. It means mini mruby compiler. Then I call the combination of mmrbc and mruby-c. It is mmruby. mruby machine is the title of this talk, whose technical stack is illustrated on the next page. We will be able to deal with almost everything about microcontroller by using Ruby. Today I'm focusing on the compiler though. Other stuff like shell and interrupt are also very interesting as well. I hope I can have another chance to talk about them in the near future. Next, I need some cross-compilation tools for ARM because the architectures of my host computer and the target controller are different each other. We use ARM non-EABI tools to build binaries for ARM processor. ARM obviously means ARM architecture, and NUM means without OS. You can also say bare metal. EABI means Embedded Application Binary Interface. So now you know these tools are what you need. I use 3 different kinds of tool chains for my project. One is normal GCC, which is a daily C compiler. Second, I sometimes build a binary for ARM Linux to make sure I didn't make a bug which appears on only ARM architecture with this. You can also use GDB to debug with QM. It is a machine emulator. And the last thing is non-EABI GCC. It is the tool for making final executable of PSOC, as you are already familiar with. By the way, I pushed a Docker image for you. Feel free to use it. The last thing of this chapter is C library. There are various C libraries out there, such as GNU C library is the most popular one though. I don't recommend you to use it for microcontroller because the code size will be too big to install. In this case, you can use GNU-lib series instead. They are designed to be small in return for somewhat abundant something like performance or runtime security. Now we are diving into mmRBC, mini mruby compiler. It's the repository of mmruby including mRBC. Please check it. These are the features of mmRBC. It doesn't depend on mruby nor mruby-c. mmRBC depends on only libc like glibc or newlib. mRBC can be integrated with both mruby and mruby-c. You can easily build it not only for ARM architecture but also many other architectures. And it is small, of course. The details are to be mentioned later though. You can install it into 256 KB ROM and runs on 64 KB RAM, as you saw on the demonstration. MRBC uses Lemon as the parser generator instead of Yak or Bison. Lemon is originally a parser generator of SQLite. I know almost all of you love a topic about parser generator, right? So I speak a little more about it. What I will say from now is what I learned as long as I could, so please correct me if I am wrong. LALR means look ahead, left to right. It is a name of the theory to parse. It is sometimes considered, I think, that Yak and Bison are almost the same. But there are several differences between them, things like Yak is non-reentrant, while Bison is reentrant and thread safe. And Yak has parser called Lexer style, while Bison has Lexer calls parser style. But you can also select all the Yak style in Bison. Lemon is reentrant and has Lexer calls parser style. It is modern style of parser generator, I think. In Yak style, the compiler calls YYParse function, which is generated from parseY by Yak. Inside that function, YYLex will be called in order to obtain next token. Then implementation of YYLex is all up to you, basically. And now you can generate final VM code with the syntax tree which YYParse made. On the other hand, the Lemon style, you would make a loop to tokenize the Ruby script. After getting a token, you call parse function, which is generated from parseY and Lemon. Then you can generate VM code as well. To summarize Lemon, it is also LALR parser generator. It is a reentrant Lexer calls parser style. According to the document, it is faster than Bison, but I don't know if it's true. And according to Mats, actually Mats told me that code size will be smaller than Bison. That's why I use Lemon instead of Bison. And then, although I don't have enough time to explain, grammar syntax of parseY is different from Bison. This is the official page for more details about Lemon. Please check it later. The final chapter, how smaller than MRBC. The only thing I have to realize is small footprint in terms of RAM and ROM. Now is that time to compare. First, we are going to check RAM consumption. In this chapter, I use MRuby3 branch of MRuby to compare with MMRBC, which I wrote. To make the comparison simple and easy, I built MRBC and MMRBC as binaries for 64-bit Linux. Both of them internally use glibc-malloc and free in order to be analyzed by Valgrind. Valgrind is a toolset that helps with doing things like profile memory, or detect race condition of multi-thread. Analysis command looks like this. We also use msprint command to see the result of massif. Here's a case 1. Put hello world contains one functional call which has one argument without parentheses, as you see. Output is obviously hello world. This is the result of MRBC. Massif shows you a transition of memory usage in this graphical shape. It tells us that MRBC used 157 KB RAM to compile Hello World. On the other hand, my compiler MMRBC used only 11 kilobytes of RAM. I believe that you are clapping now. Thank you. In case 2, we're going to compile a little bit larger script. This is the result of that script. And MRBC used 162 KB. MMRBC used 53. It turns out that MMRBC seems to have a good chance to run on one-chip microcontroller, I think. But at the same time, I think I still have to make improvement of memory efficiency. By the way, the script of case 2 also demonstrates what syntax MMRBC can deal with, such as assignment, constant, method call with parenthesized argument, array, and the assignment of array, and hash literal, symbol, string literal, and how can I say, syntax sugar, which makes array of string, and hexadecimal, unary operator, keyword true, and interpolation of string, and binary operator. My compiler can compile this syntax as of now, though I still have a lot to do, to be honest. Please check this roadmap if you are interested in. Now I will finish my talk by showing a code size comparison. These are the application code code files, what I demonstrated at the beginning of this talk. Then you can use size command to estimate how much ROM will be used. Text section is a machine code. That section contains variables which have initial values. VSS section shows a RAM size, so the total of text and data will be the size of ROM consumption. Apparently, I still have some margin to implement more syntax for PISC-5 LP, which has 256 KB ROM. Here is the summary of my talk. First, MMRBC is a mini mRuby compiler. VM code generated by the compiler runs on both mRuby VM and mRubyC VM. it is still incomplete regarding syntax and memory efficiency. MRuby machine is an integration of MMRBC, MRBC, shell, and hardware drivers. I hope that the shell and drivers, peripheral drivers, I can also say so, will be the topic next time. That's about it for today. Thank you so much for listening. I always appreciate the RubyKaigi organizers. Thank you all.
Hello, my name is Sotaro. I'm an engineer working for Square in Tokyo. I write some Rails applications, and I'm also working to improve the development environment. I developed a type checker for Ruby called Steve, and I'm running an experiment to test Steve with some of the projects in the company. I'm also a member of the Ruby committers team, and I'm working for types in the team too. And yes, it is the topic of my talk today, the state of Ruby 3 typing. So let's start with what will happen in Ruby 3 about types. Ruby 3 will ship with a feature to support type checkers. It's called RBS. It is both the name of the language to declare types of Ruby program and the name of a Ruby gem bundled with Ruby 3. The gem provides features to read, write, and process the type definitions written in RBS. The type definitions of standard libraries are included too. So you can start using the library and standard library type definitions just after installing Ruby 3. One thing I want to note is that Ruby 3 won't provide something like the standard type checker. The Ruby committer team is not trying to say, hey, this is the best type checker for Ruby code. So you need to install type checker yourself. You need to choose the best type checker for your team and your project. I'd like to introduce the type checkers for Ruby you can choose. Steve is a type checker written in Ruby. This is my project. Sorbet is the most widely used type checker for Ruby today. You may find the talks about Sorbet in the program of this RubyKaigi. Steve and Sorbet assume that the users write types to type check the programs. Type profiler is different. It tries to infer the types in Ruby programs without any inline type annotations. Mame has a talk about type profiler in this Kaigi too. RDL is another project. This is a research project, and the development team led by Professor Jeff Foster published research papers about type checking for Ruby using that tool. The papers are super interesting. If you want to read the papers, you can find them on the internet. So we have at least 4 type checkers for Ruby. Let's start with the idea of the static type checking. This is an example Ruby program. We would have several questions. There is a new method called onConferenceConstant. You may have a question that, does the new method accept a string argument, or does the method require other arguments? Like that. How about the talks method call? It uses the push method of the return value. So what is the type of the return value of talks method? It looks like an array, but it's not sure if it is correct or not. How is the each speaker method called? The method name starts with each, and we guess that it accepts some blocks. But what is the type of block arguments? Maybe an instance of speaker, but we don't know if it's correct or not. So like this, we find some questions when we are writing Ruby code, or maybe, of course, reading Ruby code. If we execute the Ruby program, the interpreter will answer to the question. It will raise argument error if the required arguments are missing. It will raise no method error if there is no method of that name. The block is a bit complicated. Ruby doesn't raise an error if an unexpected block is given to the method calls. But anyway, we will finally understand the problems if there is some problems. by running the Ruby program through tests or aspects. However, what if we went to the answer to the question without running the Ruby program? It will be a great experience if you write your code using editors or IDEs. Then some of the errors will appear right now. We don't need to run the tests, or we don't need to carefully read the source code of the library. So, static type checkers are the tools for this. It scans the Ruby source code and uncovers some of the problems without executing the code. And RBS is the data for the tools. I'd like to explain what RBS is. It is a new language to define types of Ruby programs. It is to describe API, the class and modules in the Ruby program, what methods and instance variables are available in the classes, how is the instance and mixing relationships between the modules and classes, constants, globals, blah, 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 everything about that. This is an example of RBS for the conference class. It declares there is a class called conference. It also explains that it has two read-only attributes called name and talks. Name is a string, and talks is an array of the talk objects. The initialize method accepts one string argument, and each speaker method has two overloads. It accepts a block and it yields speaker's object. If block is not given, it returns an enumerator object. Using the RBS of the conference class, we can find the answer for the questions I explained in the first example. What is the type of argument of the new method? We can see the type of the initialize method. How is the talks method? We can find there is a talks method in the conference class, and its type is an array of talk. We find that each speaker method accepts block, and it is a speaker object. The conference example is a very small example, but RBS can be used for the standard libraries. This is an RBS file for string class. This is a pretty long file, so you will find the list of the methods and the type of each method in that file. I want to introduce some of the advanced types of RBS. It has generics. The square bracket means it is a generic instance. We can write something like the array of integers or hash of string and array of integer or like this. Union types allows defining a type like string or symbol. It can be a string or symbol, but it cannot be float or hash. You can write union types in generics like array of string or integer. We also have optional types. It is a shortcut for union types with new. Integer question is an example of optional type. It can be integer or new. It allows type checkers to check if there is a possibility of calling a method on new. Interface type is to support duck typing. This is an example of the integer convertible interface. It has two int method. It means that any object can have the type if it has a toInt method. No inheritance or mix-in is required. This is duck typing. Untyped is a special type that type checker will skip any check with the type. This is same as the any type in TypeScript. You can find more examples of RBS files in the repository. It contains the RBS files for standard libraries, RBS files for the RBS library code is included too. RBS is not a very big library, but it's a real Ruby program. It's not a toy example. I believe that it's a good example of how the real-world RBS files will look like. This is a quick introduction of the RBS language. I'd like to talk about what will happen to your Ruby project. Your Ruby application should use the standard libraries of Ruby, and you may install some gems for the project. And you define some of the classes and modules for your projects. I'd like to define 3 groups of types. Types for standard libraries, types for Ruby gems, and types for your applications. The first one is the standard library types. It includes the types of the standard library classes like string or array. It will be installed automatically when you install Ruby 3. The Ruby committer team is responsible for writing them, and of course we need some help from the Ruby community. And yeah, all of the Ruby developers will use the types. Gem types is the second group. It includes the types of the classes provided in the Ruby gems. It will be written by the author of the gem, or the community will help writing the type signatures. It's essential for the users of the Ruby gems. The type checkers cannot work well without the type definitions of Ruby gems. Third group is the types of your application. This is different from the other 2 groups. It is about the classes defined in your application. The developer of the app writes the types, and it is used by the developer of the app. The writer and users are the same group of people. So the main targets of RBS are standard library types and gem types. I want to illustrate the situation that this is without RBS. Assume that there are several type checkers and they have different type signature languages. They need standard library types and the gem types. They make their own copies of the standard library types. Gem authors need to make different versions of the type signatures to support all of the type checkers. So this is not a good situation. What we want to do with RBS is to make it a common format of type definitions for the reusability of type definitions. We will provide type definitions for standard libraries in RBS, and we hope the gem authors will provide RBS for their libraries. And all of the type checkers can use the RBS files. On the other hand, the type definitions for application modules are out of scope of RBS. Type checker specific definition languages are totally okay. The developers of the application will choose the best type checker for their projects. They write type definitions for their applications, but no one outside of the team will use it. Of course, each type checker will have different strategies for the adaptation to RBS. Some of the type checkers will continue to use their native type definition languages, like the blue one in this page. Their language should have some advantages. They should provide some special features. We want them to support RBS types too, but we are not trying to duplicate other type definition formats. Or the opposite is it may use RBS for the application types to write the purple one in this page. How is the support for RBS by existing type checkers? Steve uses RBS for the primary type definition language. It reads types for libraries from RBS files, and it uses RBS for application types too. Type profiler also supports RBS. It reads library types using RBS. It infers types of your Ruby programs without type declarations. So you don't have to write RBS of your application, but it generates the application RBS for you. Thoroughbred uses embedded DSL to write type annotations in Ruby code. They have a plan to support RBS too, but it may be only a subset. Some features of RBS may not be supported by Thoroughbred. So there are some levels of adoptions, but all of these type checker supports or will support RBS. So when we explain the idea of RBS, we receive this question frequently. So why it requires writing types in other files? Embedding type information in Ruby code would be better. So I'd like to explain the background of our decision. There are several reasons. We don't want to write types in Ruby code. Matt explained his idea several times that type annotations will be outdated in future, and then writing types in Ruby code is not a good way based on that idea. I'm not pretty sure if it could happen, but I also think that it is better to keep type checking optional. I know not all of the Ruby developers are interested in type checking. They are still skeptical if it works well, and I think it's good to make it that they can try the type checkers without changing the Ruby code. They add RBS files to the repository without changing the Ruby code, and if the type checking works, it's fine. But if they don't like that, they just delete the RBS files, and the rollback is done. Another one is more technical reason. We need to support Ruby libraries written in C. Standard library is implemented in C, and there are many extension libraries. There is no Ruby code for the libraries, so we anyway need a way to write types in another file. I also want to say that types in Ruby code is out of scope of RBS. It's not included in the spec. The type checkers can use inline type annotations if they need. And honestly, we know that type checkers need inline type annotations. At least both Thoroughbred and Steve requires writing type annotations in Ruby code. Thoroughbred uses Ruby DSL for inline type annotations. It embeds method type declarations in Ruby code, and it sometimes needs annotations like t.read to specify type of an expression. Steve uses RBS for type of methods, but it uses comment for inline type annotations, like the declaration of the type of local variables. We don't say inline type annotation is a bad style or RBS is trying to replace it. It's just out of scope of RBS. It's totally up to the type checkers. So, this is an introduction of RBS language. It's a language, but it's also a library. RBS is not a static type checker itself. It's a library to help type checker and type-related tools development. So, this is an example of the components of type checkers. The list is not comprehensive. There should be something missing. But I want to say that we need a lot of work to develop a type checker. What we are interested in the most is type checking algorithm. We want to analyze the Ruby source code. However, we need a lot of work other than that. We need to define types, and the concrete syntax of the types. We have to implement parsers. We need implement many logics to validate the types or resolve type names, process inheritance, or how can we load type signatures for gems? And we need standard library types and gem types. RBS can take care of some of them. The RBS language covers these components. It defines the types and the syntax. We provide RBS library. We provide RBS for standard library. We believe that type definitions of gems will be available in RBS. And yeah, we also provide the RBS library. The gem provides some more features like this. So RBS can help doing these of works. So you can just start working for the type checking algorithms. This is a small example of a Ruby program using RBS. It loads RBS files of standard library and the files from the sync directory using environment loader. Environment is a collection of all classes loaded from RBS, and definition builder is a class to construct internal data structure of classes. And finally, it prints the type of the gsub method of string class. I want to introduce some of the features of RBS gem. Writer is to format the AST to RBS syntax. If you want to make a tool to generate RBS, you may use the class. Prototype module includes some classes to generate RBS prototypes. There is a prototype generators from Ruby code and Sorbet RBI and Ruby's runtime API. It supports writing AST in JSON format. It has JSON schema in the schema directory. So I hope the JSON format helps working for tools by other languages. So I explained that RBS is a library to help the development of type checkers and type-related tools. You would develop a tool to generate RBS, or you may want to develop new type checker for Ruby. Using the gem, you can skip working for some of the non-essential features, and you can focus on the development of core features. Of course, it depends on the design of your type checkers. Using RBS may not be the best option for your tool. But if you think supporting RBS is a good option, we believe that using that library will help you. So this is the latest update for typing of Ruby 3. Ruby 3 will ship with a feature to support type checkers. It defines a language called RBS to define types of Ruby programs. It ships with a library to read the files, and RBS files of standard libraries are included. Ruby 3 won't have the standard type checker. RBS is not a type checker, and you need to choose and install the best type checker for your project. Thank you for watching my presentation. I don't think the RBS is perfect. There are many issues and missing features. Let me know if you find some questions or any feedbacks. You can reach me on Twitter or GitHub. So thanks again.
Hello and welcome to my talk, Running Rack and Rails Faster with Truffle Ruby. My name is Benoit Dalloz and I'm the project lead of Truffle Ruby. Truffle Ruby, if you don't know yet, is a high-performance Ruby implementation by Oracle Labs. It uses the GraalVM JIT compiler to achieve its good performance. It targets full compatibility with Ruby 2.6, including the C extension. And it's open source and on GitHub. There are two ways you can run Truffle Ruby, like two VMs. So you can run it on the JVM, and then the main advantage is you can integrate with Java conveniently. And you can run it in native mode, which is the default, where the Truffle Ruby interpreter and the Graal compiler are compiled ahead of time to a native executable. So this is like the end result is a bit like MRI, like you have one executable with everything in it. And this provides faster startup, faster warm-up, and lower footprint. And the reason is basically you have a VM specialized for Truffle Ruby with nothing else. It doesn't need to be as generic as a JVM, doesn't need to load classes dynamically. No, it's just like running Truffle Ruby, and that's what it's specialized for. In terms of compatibility, Truffle Ruby is getting pretty good. It targets 2.6, and many C extensions work out of the box. So OpenSSL, Zlib, Reaper, Nokogiri, many database driver, and so on, they just work. And there's a good chance that if you try a random C extension, it might just work on Truffle Ruby. And this is a big advantage. Like if you want to try your existing application on Truffle Ruby, if you come from C Ruby, probably it will work without changes to the gem file or very minimal ones. In terms of completeness, according to Ruby spec, Truffle Ruby passed 97% of the spec, which is quite good and actually the best ratio for all Ruby alternative implementation. One of the big Truffle Ruby goals is to run Ruby code faster, and Truffle Ruby is already doing great on many CPU-intensive benchmarks and on micro benchmarks. But what about web application, right? This is what we look at today. And Truffle Ruby wants to run your Ruby code in parallel and doesn't have a global lock, so that works well. That works great. But for C extension, the situation is a bit more complicated. Because some C extension expect to run all their C code under a single lock, we actually have a global lock enabled by default for maximum compatibility. And then GraalVM as a project provides new tooling that works across languages. So we have, for instance, cross-language debuggers and profilers and so on. As a simple example here, we have the CPU sampler, which is a sampling profiler. And to run it on Truffle Ruby, it's really simple. You do Truffle Ruby minus CPU sampler, and then your program. And what it gives is like this report at the end of when the program ends, it gives you like how much time was spent where, including like how much of it was in compiled code, how much in interpreter, and so on. So today I will look at the Rails Simpler benchmark, or RSB, which is a project by Noah Gibbs, who did a lot of benchmarking on Ruby 3x3. And so Ruby 3x3 is therefore to make Ruby 3 times faster than Ruby 2.0. And RSB consists of two things. So there's a simple rack application and a simple Rails 4 application, with both of them with various routes. And it's a Rails 4 application because Noah wants to compare to Ruby 2.0, so you cannot use the latest Rails for that. They both use WRK to benchmark like how fast it is, the throughput and the latency. And of course, it provides a harness with various configuration in which you can configure almost everything. So here we have to focus on a few things. And what we decided to benchmark in this talk is the rack application with a simple ERB template, which comes from the C Ruby benchmark, and the Rails 4 application serving a plain response, which is the default for RSB. And both of these will run on Puma, which is a well-known web server. So we measure two Rubies here. We measure Ruby 2.6 because the version that Truffle Ruby is compatible with right now, and the latest Truffle Ruby in JVM mode, because the JVM here is a bit faster than in native mode. I also wanted to try the latest JRuby, but that didn't really work because there's a bug in JRuby when using JRuby with Puma and keep alive connection. Basically, JRuby seems idle, and is like extremely slow. So yeah, there's no point to report this number because there's just like, yeah, it's clearly a bug. It's unfortunate though it's not been solved because like this is known for more than a year now. And then yeah, but the only thing we could do is okay, don't use keep alive connection, so create a new connection every time. But this is a huge overhead, and and if we do this, we end up benchmarking basically the kernel and the network stack more than Ruby. So that's not interesting. So we have 3 concurrency settings here we can tweak. There's the number of server threads, or actually you can also use processes on Ruby. And then there's a number of WRK request threads and the number of connection inside WRK. And here, to make it simple, we use the same number for all, which means we use the same number of requests and server threads, so they just match each other. And each request thread maintains 1 connection, so it's very simple on the WRK side. And one of the goals of using this is that we avoid extra processing on both the WRK side and the server side. So really focus on like, how fast can we process 1 request. Run this on an 8-core processor and actually kept frequency scaling and turbo core or turbo boost enabled. Because just that what happens on real server, like they don't disable this because it's just like more efficient, right? And what this means is like when you go to many threads, you don't have a perfect scaling because simply like one more CPU run, the maximum frequency reduces to avoid overheating. Always that show our peak performance. So basically, running a request until the server is warm, until the number of requests becomes quite stable. And the reported numbers are in requests per second, and each run is from WRK. So it runs for 10 seconds, then it knows how many requests it managed to do in that time, just divides it by 10, and that's it. These are very small rack and rails applications, so they probably do not represent well real application. And keep in mind that conditions for measurement are ideal. Like there's just 1 request after another, it's very nice. And the real world, of course, might be very different than that. So let's start with rack. So here we have a small ERB template, if you remember. And what we see is Ruby starts here at 20,000 requests per second. It's per rack, right? It's very minimal, but still quite impressive. And then the issue is like as we go with higher number of threads, for Ruby, it just becomes slower because this is global lock, right? Threads are not really useful on Ruby, at least when there's some CPU work here. And like even though like you would think, hey, there's a lot of I/O, well, you still need to parse the HTTP and then generate the HTTP response and everything in the middle with all the middleware, right? So in the end, here is still quite CPU intensive. And so yes, Ruby with thread doesn't do well. On the other end, if we look at, if we look at Truffle Ruby, we see it's over 30,000 requests per second, which is quite good. And then it just scales up with more cores. Of course, what you could do is you could run Ruby with multiple processes, and that gives you this. And that looks a lot better for Ruby now. I mean, Truffle Ruby is still quite ahead with like almost 20,000 requests more every time. But yeah, I mean, that's cool. You can do this. On the other end, when you have multiple processes, you also have quite a few disadvantages. Or if you turn it around, you have some advantages of using threads, like a single process with threads instead of many processes. Like for instance, if you need to just-in-time compile the program, if you have threads, you only need to do it once. If you have a process, you need to do once per process. If you have common data structure, either at the virtual machine level or at the Ruby level, for instance, in some constants or whatnot, they're always shared by threads. You control what is shared, and it's very easy to duplicate. On the other end, if you have processes, you need to rely on fork. If you don't have fork, it's simple. Then you just multiply the memory footprint by the number of processes. If you use fork, you hope that copy on write will work well enough. But sometimes I just touch a memory and we'll end up duplicating a lot of things. And so overall, like your heap become more and more fragmented and shares less and less. Of course, if we don't use fork, you cannot have the fork pitfalls. So for instance, like one of the well-known one is like when you fork, you actually inherit all file descriptors. So if at the point you forked, you would have a connection database, that would be a big problem, because now like there are two processes that would share the same connection, and they could just like, get the wrong one, get the wrong response from the database. And then of course, like the obvious thing, like we don't have to manage multiple processes, just one. So it's a lot simpler. Don't have to think about all this extra interaction between processes. And finally, if you need to communicate, or if you need to synchronize between threads, it's much faster and it's much easier than between processes. Like try synchronizing between multiple processes, it's extremely complicated and it's very slow. So let's have a look at Rails. So here we have the CRuby with threads and with processes, and TruffleRuby again. And CRuby again with more threads, it just becomes slower. And as the baseline, it's reached almost 3,000 requests per second. This is a plain response for Rails, right? So that's why it's quite fast. But then TruffleRuby reached like 6,000 requests per second. That's, I think, quite impressive. It's like a 2x speed up on one thread. And then as you keep scaling up, TruffleRuby like keeps a good way ahead, and reaches here about 18,000 requests per second. So I have to note a few things here. So the benchmark here I showed they run with the C extension log disabled. The only C extension here is the Puma parser, the Puma HTTP parser, and that one is safe to run in parallel. And this issue, like whether we can run a C extension in parallel or not, whether the C extension needs a global lock, that's something that actually will come as well for Ruby 3, for the Raptor project by Koichi. Basically, for C extension to work in multiple Raptor, you will need to mark them as thread safe or can be executed in parallel. And basically, TruffleRuby is kind of the same thing like this. Like, does this extension have its own synchronization for the state at the C level or not? And actually, for TruffleRuby is less restrictive for Raptor. Like, for instance, you cannot pass object between different Raptors, non-shareable object. But in TruffleRuby, you can. That doesn't matter. The only thing that matters is like when you have a global variable in C, do you probably synchronize access to it, and so on. And yeah, this is something we want to work on and to make it easier to mark C extension properly as safe to be executed in parallel. And then another thing we did here is like there's a splitting limit in Truffle. By default was just like too low for Rails. Basically, like Rails is still quite a big code base, right? So even when we run this in plain response, we're already like above the splitting limit. So here we need to tweak it. And yeah, the thing is, of course, we want to fix this so we don't have to touch this limit in the future. But actually, like we probably want to remove this limit because it just doesn't. Yeah, there's another limit that grows with the size of the code you load, which makes a lot more sense than this hard limit. And what splitting does is basically, suppose you have multiple call to map in your application, to array map, for instance. Then basically it will make a copy of map for each of the call site. So what this gives you is then when you just-in-time compile map, there's the loop inside of map. You can compile that together with the block it's given, and then you can optimize them very well together. But if you don't split, basically you would have a single copy of map that's compiled, and it calls 1,000 blocks. It calls 100 blocks around all the app where it's called, and that would be very inefficient. So splitting can be quite important for Ruby. A small reminder about the results, like this was very small rack and Rails application, and the conditions for measurement were quite ideal. So what I would recommend you is to benchmark your own application, and if you can, share the result with us, whether they're good or whether they're bad. If you want to try TruffleRuby, it's really easy. You can use your favorite Ruby manager, and then you will get TruffleRuby in native mode. So you can use Ruby install, RVM, RVM, and so on. And you can also use GraalVM, and then you get both the native and the JVM mode. And you can just get it from the website and install the Ruby component. What you get with GraalVM is you also get other languages. So you can interoperate with Java, but also JavaScript, Python, R, and all the LLVM bitcode languages, so C, C++, and Rust. and even WebAssembly recently. So all of this run in a single VM, so you can very efficiently call a function from one language to the other. And you can inline through it and so on. And this is actually how we implement the extension in Truffle Ruby. And that concludes my talk, and thank you for listening.